So once you are able to identify your electron donor, let's look at this particular example. In this example, remembering counter ions, which of your molecules, this one or this one, is going to be your electron donor and why?
The first one.
Okay. And so why is the first one your electron donor?
Because the oxygen has a negative formal charge.
Very good. So because of the counter ion effect, the metal ion will get a positive charge and the atom next to it will get a negative charge. This formal charge will help make this oxygen the basic site. And so this is your base. For this HCl, there is only one hydrogen which is attached to an electronegative element, making this your acidic site and this molecule as your acid. So what is the next thing that you have to do? The next thing that we have to do here is, after we have labeled our acid and bases, after we have figured out our site of acid and bases, the next step is the reaction mechanism. So the base, who's the electron donor, will attack your hydrogen. There is a bond between hydrogen and chlorine. The hydrogen will leave the electrons behind with the atom it is attached to. In this case, it is chlorine. So what is the new product that we see form?
H2O.
H2O, very good. And so I have this OH and I have this
LiCl.
hydrogen right here. Yeah. What is the other thing that is left behind? What we are left behind with is this chlorine with the negative charge. And to balance out this negative charge, we can use this lithium ion. In other words, we can just write lithium chloride. Okay, we don't have to write lithium plus and Cl negative. But if you want to do that, that's completely fine. Actually, that would help you figure out who among these two is your conjugate base and who among these two is your conjugate acid. So what is going to be your base? The
Conjugate acid.
Who is going to be your conjugate base?
Is it the lithium chloride? Because
it is the lithium chloride because of the excess electrons on it. Plus, if you look at this, there is an excess acidic hydrogen here or excess hydrogen. This base has produced a corresponding conjugate acid. So the base had no hydrogens. I'm sorry, it has hydrogen, but not excess hydrogens. But now your base has excess hydrogens, making it the conjugate acid. So recognizing our electron donors is usually easy. If you look at the options available here, oops. Anyone who needs to copy this? Okay. If you look at the options, we didn't even need to see the options. We had written out the answers by ourselves. But the main idea is for you to be able to recognize your products. So what is it that I am expecting from you? What I expect from you is to label your base and your acid, to mark your basic site and your acidic site to show me the two-step chemical reaction and to show me the products HOH, lithium chloride, and then show me who's the conjugate acid, who is the conjugate base. The last thing that you can do is tell me the direction of this reaction. Now looking at the base stability, which base will be more stable? The O negative or the Cl negative? Remember oxygen, remembering our periodic table. CnOF, chlorine. So chlorine is a bigger atom than oxygen. Whenever you're going or comparing electronegativities and size, all of these atoms are similar sized atoms. So what matters in this according to in the period is the electronegativity. But when you're going from top to bottom, the electronegativity is decreasing, but the size is increasing. So bigger size means that the negative charge will be stabilized better. So this is a more stable conjugate base. Wherever your base is stable, that is the direction of your reaction. Okay, because down the group, it's not electronegativity, it is the size which will win the race. Remember, whenever we are thinking about the base stability, you have to think about stabilization. What stabilizes? Spread of electrons. It could be through resonance, it could be through induction, it could be through orbitals. All that matters for your stability of base is spread of electrons. The more spread of electrons the base feels, the more stable it becomes. And that's the purpose of doing all the chemical reactions. Unstable want to become stable. That is the point.
Okay, so I just have a quick question.
Go ahead. Yes, please.
So the arrow is going to the right because the base, which is the lithium chloride, the chloride has more electrons than the O in lithium hydroxide, right?
No, it not just has more electrons, the spread of electrons in that big atom will be better.
Right, okay.
And this will be like a small atom where the electron spread is there. It's concentrated, more localized kind. But in this Cl negative, the spread is to a bigger area or a vast area, if that makes sense.
Yes, it does. Thank you.
Hold on. Nobody told me I did not remove my periodic table background. Were you all able to see clearly though? I mean, okay, I'm glad you were. So these are the things that I would expect on each chemical reaction that we are doing. Anybody who feels uncomfortable, don't feel shy. This is a time that we help each other. Anybody who needs to copy this?
I have another question.
Go ahead, Sydney. First of all, let me just delete it and move forward. Anybody has any questions here except for Sydney? Sydney, do you have a question on this slide or in general?
Oh, it was just a clarifying question. So in order to get this question right on the drill, you would want us to draw the arrows to which the electrons are moving to, and also the direction of the
Yes. So when you draw these curved arrows, that will be part of your reaction mechanism. when you draw this straight line with the arrow, that would indicate to me that this is the direction of your reaction. Sometimes on your exam, you might also see a arrow like this, which indicates that overall your reaction is going in this direction. Does that make sense, Sydney?
Yes, it does. Thank you.
Okay, very good. Okay, anybody else wants to copy from here or anything? All right, very good. So all of you are feeling comfortable? Can I ask anybody any question? All right, let's do the 9th one and let me choose a volunteer for my help. Ariel, first on my list. Are you here, Ariel, or? Oh.
Yes.
Okay, Ariel, don't be scared. I'm here to help you. And everybody here is as
I
uncomfortable.
have a lot of noise in the background right now, but I'm paying attention.
Okay. So Ariel, what is the first thing that we are going to figure out?
You have to identify the acid or base.
Mm-hmm. Which out of these structures will be your base, the electron donor? Okay, let me ask you that way. Do you remember all the 3 electron donors? Ariel, can you just say them out for me?
Wait, can you repeat that?
Yes. So what are the 3 types of bases that we have, or how you identify the 3 electron donors?
The Lewis, wait, I'm a little confused.
Mm-hmm. When we talk about bases, what are the 3 kinds of bases that we look at? Yeah, look on your screen.
So it has a negative charge, a positive charge, or lone pairs.
There is no positive charge. Where is the positive charge?
So it's just negative and lone pairs?
Oh, yes, yes. The negative charge, the lone pair, and what is this?
The pi minus electrons.
The pi electrons. It's not pi minus. I just put a hyphen here. So again, tell me, what are the 3 base donors? Mm-hmm. Don't be scared, Ariel. Don't feel flustered. Just stay calm. Negative charge, yes.
Negative charge, lone pairs, and pi electrons.
Very good. So looking back on these 2 structures, a negative charge or a lone pair or pi electrons. Ariel, out of these 3 sources, which is the strongest electron donor source? Mm-hmm.
The negative electrons.
The negative, because it has the excess of electrons. Very good. All right, that's more than enough. I was not trying to tease you. I just want all of you to be on board. Okay, thank you, Ariel. Let's see if I can find someone else. Nia Hayat. Hayat, are you here?
Hi.
Yes, Hayat. So we have identified the 3 sources of our bases. Out of these 2 structures, which might have the base that we are looking for? Now, I want to give you a warning here, Nia Hayat. Remember your counter ion effect. Okay, just think about that and tell me, out of the first and the second structure, which can be your base and why?
I think it's the second structure because the oxygen is connected to a metal ion, the potassium, which will cause it to have a negative, like a real negative charge. instead of
Very
like a
good.
partial. And then, so that means it will use that charge to accept the hydrogen or the electron.
No, it will donate electrons. Very good name.
Oh, because this is Lewis? Is it because it's Lewis acid and bases now?
So bases are always electron donors. Okay, and this is the Lewis definition. But the Lewis definitions are so broad that they can accommodate the Bronsted-Lowry definitions also. Okay, so internationally, worldwide, we always use the Lewis base definitions, which is the electron donation. We always look for base not as a hydrogen acceptor, but as a electron donor. Okay, hi. Well, thank you for your answer also.
Okay.
Very good. Does that make sense to everybody? There is a potassium ion here, and the potassium ion will give you the plus charge, making this oxygen very, very basic in terms of electron donation. So I'm going to label this oxygen as my basic atom and this structure as my base, this molecule as my acid. Who can tell me where is the most acidic hydrogen and why is it very acidic? Okay, it's
With oxygen,
what? I'm sorry. Where is
OH,
the atom?
OH.
Yes, so this hydrogen is the acidic site. Okay, very good, Tammy. And so when we will do our chemical reaction, the electron donor will go and attack this hydrogen. The oxygen hydrogen bond will break. So let me redraw this here. So I just did this here. From the electron donor, I will go and abstract out my acidic hydrogen. Hydrogen will leave, breaking the bond with oxygen, leaving all the electrons with my oxygen. How am I going to write my structure? There is the CH3 with the C double bond O, and this oxygen with what? This has my acidic hydrogen from acid. So the bond has been broken. What is left behind this particular structure? Oh, there is a CCl3 also. Okay, instead of CH3, this is a CCl3 group. Carbonyl with my O negative charge. So what will balance out this O negative? Anybody?
K.
Okay.
The K positive. So let's try to recognize the rest of them. I have my acid, I have my base. Which out of these two is going to be my acid? Let's see who can help me.
OH, conjugate acid.
Oh, I'm sorry, which one are you saying? The OH
The,
is
the first one, conjugate acid.
very good. So this is my conjugate acid, and because of the electron donor, strong electron donor right here, I will have a conjugate base. So which two materials have I identified here? I have this and I have this as my products. The last thing is which direction the reaction will go. So I'm going to ignore my acids. I will only look at my bases. So if you look at this base and if you look at this base, I'm not going to write all of it. CCl. So this was in my products, and the first one is in my starting materials. I want all of you to redraw this somewhere because I'm going to show you resonance structures. Remember, we are going to compare the base with the conjugate base. Who out of these two is more stable and why? In our starting base, is there anyone who wants me to wait for them? Nisha, did you copy? Misha Ren, are you here? Oh, she's not here? Oh, never mind. So you have a allylic kind of a structure, right? So your new bond forms here. The CO bond breaks here. And this is the new resonance structures. So two resonance structures. And this molecule is stabilized by resonance. So we say this is resonance stabilization. Okay. But on the other hand, if you look at the conjugate base, it has exactly similar resonance structure. However, this conjugate base has additional electron withdrawing groups, which will pull electrons. And if you carefully look at this system, the chlorine and the carbon and this carbon, the carbon and this oxygen, and the carbon and this oxygen, all of your molecule is resonance and induction stabilized. So how do we determine the stability of a base? The more spread of electrons that structure feels, that is how we figure out if a molecule is more stable than the other. Anybody who does not understand this?
I have a question.
Go ahead, Sydney.
I get the resonance. I just have a question about the induction stabilized. So is the induction coming from, you said the pull between the two carbons because of the Cl?
Yes, the electronegative Cl.
So that has to do with like the dipole thing?
Yes. So it is pulling the electrons.
And that's what induction, like when you're talking about induction, you're talking about like the dipole stuff, right?
So yes. But when we talk about induction and dipole, induction definitely has a dipole associated with it. But when we talk about induction, we usually think about the push and the pull of electrons. Okay, it's not actually, definitely the CCl is a dipole. There is a dipole. It is a polar bond. There is no doubt about that. But when we're talking about induction, we are actually thinking about the pull of electrons. All of the structure is feeling because of one chlorine, two chlorines, three chlorines. So this pull of electrons throughout the group is actually spreading throughout. So this spreading throughout of electrons is what is causing further stabilization of this conjugate base. Sydney, does that make sense?
So because there is like electrons pulling on the right side, but they're being balanced by the chlorine electrons pulling on the left, that's induction stabilization.
So there is no balance. Look, this is carbon. Carbon is tetrahedral. Right? So if the rest of the molecule is somewhere else, and even if you think that this is the dipole, and that's completely fine, there will be a resultant dipole. But we are not talking about a resultant dipole. We are talking about the spread of electrons, or this is just, towards the structure or towards a bond when the electrons can move from this carbon. There was this, let's redraw this, all of it. So, when you have in dipoles are fine because that you will have a overall dipole or a resultant dipole. I'm not talking about just dipoles. I'm talking about the spread of electrons through the bonds, through the sigma bonds. You see? So from this carbon, electrons are being pulled towards chlorine. There is no vacant orbital. There is no positive charges. There is no negative charges, no formal negative charges or anything of that sort. There is just a pull of electrons along the sigma bonds. So dipole and induction are very closely related. You can say that, but they are not exactly the same thing. I hope that makes sense. Yeah, are you still confused?
Yeah, so why didn't the other molecule have induction stabilization?
Oh,
What exactly
carbon.
is?
Because there is hydrogen. Chlorines are electronegative elements or electron withdrawing groups.
But
So
you can't say that the oxygens are causing the dipole?
So there is definitely, but this is same. This is exactly the same system. This part is exactly the same. They had similar resonance. When the oxygen made a new bond here and broke the pi bond here, it did do that exact same thing on this molecule also. So the electron spread was only between this oxygen, this carbon, and this oxygen. Right? But in this particular example, the electron movement is not just on this oxygen, this carbon, but from here to this carbon also. These chlorines are pulling electrons from oxygens and carbons in, wherever they are. Of course, as the distance will increase, the pull will decrease. Let's say you have this molecule where the fluorine is at the end, and then you have another molecule where the fluorine is at the next carbon. Where do you think will the more pull of electrons will be felt? Where it is close or where it is far?
Close.
Where it is close. So, as the distance will increase, the pull of electrons, the spread of electrons will also decrease. So here, all of these are involved in pulling electrons. But here, it might just end up here. You see what I'm saying? We don't know. I'm just making this number up. Because the fluorine is too far, these electrons from oxygen may not feel that pull that much. They are feeling it, but not that much as it would when it is close to it. What did I do? Are you still
Okay.
on the screen now? Oh, what am I doing? What am I doing? Yes, please go ahead. Tell me.
Okay, so you're saying that the molecule on the top right that has a circle around it, that is demonstrating induction.
Better.
Yes.
A better induction than this one.
Well, okay, but you wouldn't say that this is not experiencing induction. This is just the other one's stronger.
Yes, exactly. Exactly.
And
It is
then,
experiencing induction. So if I have to, that's a very good question. If I have to ask you, so I have these three. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. All of them have 5 carbons, exactly similar carboxylics. On one of these, I have a fluorine at my 5th carbon. On one of these, I have my fluorine on the 4th carbon. On one of these, I have my fluorine on the 5th carbon. Out of A, B, and C, who is going to be the most stabilized conjugate base and why?
A, because it's the closest, so it'll experience the strongest electron pull.
There you go.
Okay, so I still have a question, like,
So
because
this is the most stable base. Its starting acid will be the most acidic. You know the corresponding acid that they will have? The A would still be the most acidic. Most stable. So remember, whoever has the most stable conjugate base will have the most acidic hydrogen or acid.
okay.
Go ahead, Nia, yes.
So back on that other picture where you had the one that wasn't experiencing induction,
Oh,
stabilization.
right here.
So yeah, so earlier I used the word balance, but like I mean that in the sense like the way that so the one with the hydrogens in the top left.
I know you're. What balance?
So what I'm trying to understand is like they both have dipoles electron pools, and you're saying that the electron pool is, the induction stabilization. And so if the one with the hydrogens has an electron pool and the one with the chlorines has an electron pool, the only difference between these two is that the one with the chlorines is being pulled in all directions. It's being pulled on the right and then balanced by being pulled on the left. But the one with the hydrogens is only being pulled to the right.
This pull, yes, this pull is causing the spread. Yes.
Okay, so without the spread, without the pull in the other direction as well, it's not going to be induction stabilization.
No.
Okay, got it.
Okay.
Thank
good.
you.
Good. You're welcome. Anyone else? Any other? One else has a doubt about this? And so, oops, what did I do? If we look back at this, the reaction will go in the which direction? In the direction of our most stable conjugate base, which is this one. Right? So we get the CH3COH and the potassium ion right here. Conjugate acid, oops. This is my base, this is my acid. And you will have to show all those atoms, the sites and all that. Okay, everybody feeling good about this? Not yet? Almost. Okay, let's look at another example. So this is right here, your lithium ion, which will help you recognize your counter ion. Portia, go ahead. Oh, was it an accident? And so this reaction is a very important reaction and you will have to memorize it to heart. You will have a sodium kind of a metal. What is next to it is carbon. And if you look at this and you look at this, Who out of this, one or two, will be your electron donor?
The first one, base,
Why? Why?
because Na C is negative.
Exactly. Very good. Good job, Sammy. So because of this positive metal ion, the counter ion effect, the C will become the negative charge. There is no other carbon with donor electrons. And so this is your base. Where is your acid? This is my acid. Which of these hydrogens will be my acid? The sp3 carbon or the sp carbon? Elizabeth Chapman, are you here? Elizabeth, you can go ahead and unmute yourself. Elizabeth, I'm asking you to unmute on your screen also. Did you see that request?
What's the question?
Yes, thank you for unmuting yourself. Among these two choices that I am showing you, there is a sp3 carbon and a sp hybridized carbon. Which of these hydrogens will be more acidic?
Wouldn't it be SP3?
No, so remember your ARIO rule? The atom is the same, both of them are carbon. There is no resonance, no induction. So you have to follow orbitals. So what did we see yesterday about orbitals? Who will make a more stable conjugate base? Do you think this will be a more stable conjugate base, or this will be a more stable conjugate base? This will be a more reactive base. The sp orbital will stabilize your electrons. So this will be my less stable conjugate base. Now tell me, Elizabeth, out of this sp3 or this sp carbon, which one will be the more acidic one?
Wait, I said SP
Okay, and why?
because it's more stable.
What is more stable? The
Carbon.
Conjugate base of this acid. The conjugate base of this acid is more stable. Okay? Very good, Elizabeth. Thank you for answering this. And so this is our base with the carbon. This is our acid. We are going to do our chemical reaction. The base, the negative electrons, will go and abstract out the hydrogen. They will break the bond between hydrogen and carbon, and I'm going to get the conjugate base. Where will the sodium ion go? The sodium ion will go and neutralize this C negative. What is left behind? This carbon with
Hydrogen.
H3s, and then by tomorrow we will learn this name. Your hydrogen has gone here. So this molecule and this molecule. So where is our conjugate base among the green or the brown? if you look on the screen, which is your conjugate base? The green molecule or the brown molecule? And
The brown.
Why?
Because it has that negative.
It has the excess electrons on it. This is our conjugate acid. The next part is prediction. You do not need to look at the acids. You just need to look at the conjugate bases. Now, the problem with this base is it has plus I effect. What is a plus I effect? For a change, it is getting electrons from all its surroundings. Remember, all alkyls are positive inductive effects. They push electrons away from them, making this carbon super electron rich. Electron rich, less stable. So the concentration of electrons is on the carbon. The electrons are localized, not delocalized, not spread out. On the other hand, if you look at this conjugate base, the sp orbitals will stabilize the negative charge, making this conjugate more stable. So when you will come for your drill test, I will ask you, out of these two conjugate bases, which is more stable and why? And you should be able to give me the answer that this is more stable because the orbitals help stabilize the negative charge or something on that line.
And it's more stable because of the triple bond that C is
No,
bonded.
no, not the triple bond, the sp orbital.
Oh, the SP.
Yes, the sp orbital helps stabilize the negative charge. Sp orbital has 50% s character. What does that mean? It means that the electrons are close to the nucleus, not everywhere in directionals. You know, when you have a p orbital, you have a directionality associated with it. But when
So
you have
the
an s orbital, which is spherical, there is a spread of electrons in all directions, but close to the nucleus. Go ahead, Sydney, you were saying something?
So the sp orbital is more stable than like the sp2 and sp3.
Exactly. That's why the sp carbon hydrogens are more acidic than sp2 carbon hydrogens than sp3 carbon hydrogens. So this is the REO that we did. This is the orbitals part of the REO.
That is more acidic too, as well. Is that what you
So
said?
because it is more acidic, the sp is more acidic than sp3. Why? Because the conjugate base of this will be more stable. That's the only reason. Why will it be more stable? Because the sp orbitals help spread the electrons on it. Whenever you're looking at base stability, always look at electrons being spread out. Hi, did I answer your question or?
Yes, it did. Yes. Yes.
Okay.
Thank you.
So overall, this will be the direction of your reaction. All right, very good. So